Hello everyone, I'm Masaki Waga at National Institute of Informatics. Today I'm gonna talk about falsification of cyber-physical systems with robustness-guided black box checking. So, it is important and necessary to test a cyber-physical system, for example a self-driving car, before deployment because the problem in these systems, for example a car crash, has a very big impact on our daily life. Testing is also important during development because like this kind of loop continuous integration is known as very good in practice for the software development, and I think it is also important and very useful for the development of cyber physical systems. So testing is important for development as well as just before deployment. And one way to do a testing for cyber physical system is falsification. Falsification consists of this kind of loop, and the essence is robustness with optimization. So, in falsification, in this loop, first, this optimizer generate this initial input signal. This signal shows, for example, how we change the acceleration, the accelerator pedal of this car, for example. And then this input signal is given to this system model, this Simulink model, for example, and it generates this kind of output signal. So this M signal can be, for example, velocity, how velocity changed. And this output signal is given to this robustness monitor. And here the specification is given in signal temporal logic, but this monitor interprets this output signal, and then it says that the robustness is 30. It means the satisfaction degree of the given specification for this output signal is 30. And then this optimizer tries to minimize this robustness. And for example, by giving this robustness 30, this optimizer may generate this second input signal, and then this is given to the system again, and then we have this output, and finally we obtain this robustness, which is minus 10. And when the robustness is less than 0, it means that the given specification is violated. So we can falsify. In other words, we can find an input which causes a violation of this system. We can generate such an input signal by using this loop of falsification, by using robustness and optimization. And this is the robustness of STL. So in the usual Boolean semantics, what we have is just safe. The specification is satisfied or violated, but by using robustness, we can say that, okay, this one clearly satisfies that, but these two things are satisfied or violated, but these two are really close and near the borderline, or this kind of discussion is possible with robustness of STL. So this is the summary of falsification. This looks good, but falsification has one issue, which is falsification is one shot. So in practice, it is very often the case that we want to test many specifications. For example, we have here specification 1 and 2, but in falsification, these loops for testing specification 1 and this loop for testing specification 2, these two loops are actually independent. It means that the information in the above loop is not reused to this loop. Okay, but maybe we can share some rough idea of how system behaves, for example, but this kind of things is not shared. So there's no reused information between these two loops. So this can be a potential point for the optimization, for the efficiency of falsification. And a similar thing happens for this thing. So especially for the continuous integration, it is often the case that we want to test one system for different versions for many times. For example, we first tested version 1, and then we modified some part, and then we want to test the second version. So this kind of thing often happens, but here it is probably the case that the important input for the version 1 is also important for version 2. So yeah, so once we know that what kind of input signals are really important for testing version 1, then we want to reuse that information for this version 2. But yeah, since these two loops are independent in falsification, we cannot do that kind of things in the usual loop of the falsification. So the question is how to reuse the previous exploration information in the falsification or the testing of cyber-physical systems. And our approach is to use black box checking. Black box checking is this kind of loop, consists of automata learning, model checking, and some testing. And roughly speaking, it is like at first we construct an approximating model, which is an automaton, from the actual CPS model, for example, a Simulink model. And then, by using this automaton, the approximating automaton, we do a model checking. And then, model checker returns some answer, like the specification, the given specification is satisfied or violated. And then, we do a validation of this approximating model, which is an automaton. Yep. So this is a rough idea of the black box checking. And since this black box checking is a testing method, it outputs if the given specification is satisfied or violated. But also, black box checking also outputs the constructed approximating automaton. And we can reuse this automaton for the next specification, nor like we can exploit this information for the second version of the system, for example. Yeah. And here in black box checking, we have these 4 components, but actually the most challenging part is this part, to check if the Simulink model is close enough to the approximated model, automaton. Okay. So this is called equivalence test. So in theory, automata-based conformance test should be fine because like we have a soundness result. But for the soundness, we need the number of the system states. So yeah, it is usually something we don't have. So this is a problem. And in practice, it is known that random test works very good, but yeah, it's not good at hitting some rare counterexamples. And yeah, and also like we want to have more stable results rather than random tests. In that case, we want to do something other than the random testing. So yeah, but actually in the usual falsification literatures for cyber physical systems, what we use is to use robustness and optimization. So now question is, can we do this kind of thing also for the black box checking? So this is our contribution, robustness-guided equivalence test for the black box checking. So yeah, here what we did is the equivalence test by using robustness and optimization. Yeah, basically what we do is to test if the approximating automaton behaves similar enough to the Simulink model by searching for this kind of input signals. And we use genetic algorithm or hill climbing. And yeah, and we use robustness of STL for the fitness function. And I will explain later, but actually we do not directly evaluate the automaton. And yeah, this is, I think, good, but I will explain the detail later. Alright, so in summary, now contribution can be summarized in this way. So we presented robustness-guided equivalence testing. We also introduced a new robustness of signal temporal logic suitable to model checking, but this is more like a technical detail and I will omit this part in this talk. And then I used this equivalence testing for the black box checking of cyber physical systems, and our experimental result shows that it outperforms the baseline for the efficiency. Alright, so let's go to this black box checking. This is mostly preliminary, but it all includes some techniques I used. So black box checking consists of automata learning, model checking, and equivalence testing. So, yeah, as I said before, black box checking consists of these 4 components. At first, we learn an automaton from the cyber-physical system, for example, a Simulink model. So it's done in such a way. So first we obtain suitable input and output pair of the actual system. Then we generate a candidate Myhill-Nerode equivalence relation, and then we construct the corresponding millimassing M. So this is something we usually do in the automata learning literatures. For example, Elster algorithm also. Yeah. And then what we do is to do a model checking. Yeah. Here is have some difficulties because like this given phi is not LTL formula but STL formula, but the usual model checker doesn't accept STL. But now our solution is to use this STL formula as an LTL formula. This is because like the syntax of STL and MTL are almost the same. It has this kind of minor difference, like in STL, this kind of inequalities are used, while in LTL, these propositions are used. But basically, these two things are really close. And in order to have a good correspondence in the semantics, we assume that the signal is discrete time with constant interval sampling. But under this assumption, it is okay to just use LTL model checker for verifying STL formula. So this part is fine for this technique. And then this model checker says if this specification phi is satisfied or not. Okay. And if this is violated, it also returns a counterexample U, this one. So this counterexample is something like if we give this U to the automata, the approximating model, then it violates the given specification. So then what we want to test is if we give this U to the actual system, for example, the Simulink model, is it violating the given specification? If it is a case, this is the end of the testing because we found falsifying inputs. But otherwise, we use this difference. Like if this U doesn't cause a violation of in the original system, it shows that this original system and the approximated automaton, these two things are different. So we use this information to refine this automata learning part. Okay, it's good. And yeah, in order to test this, what we have to do is basically just to do a simulation, just to run a simulation and check the satisfaction. Okay, and in case this model checker says that this phi is satisfied, this approximating model, what we have to do is to test if this automaton is a good approximation. And this part is, as I mentioned before, the difficult part and our main contribution. Alright, so then let's go to this robustness-guided equivalence testing. The idea is to use robustness and optimization. So this robustness-guided equivalence testing consists of these loops. First, we generate population, this U. This is a set of the candidate input signals. And then for each input signal U in this large U, in this capital U, we test if this approximating model and the actual system, these two things output the same. And otherwise, this is the counterexample for this equivalence. But if these two systems behaves similarly for each of these input signals, we generate the next populations. So in the genetic algorithm, we use the standard crossover and mutation, and in hill climbing, we just take the neighborhood points. But then we generate the next candidate populations, and then we do the selection, which is also something really similar to the usual genetic algorithm. But here, we take the input signals such that the robustness for the actual system is small. So here we do not evaluate the approximating model. So this is one point in this algorithm, in this equivalence testing. So yeah, so why we can use this function as a fitness? So first, we assume that the actual system M violates this given specification. In other words, there is an input signal which makes the robustness negative or zero. Yeah. This is because like otherwise what we have to do is just say, okay, this is fine. And we have this fact. So the approximating automaton satisfies the specification. In other words, for any input signal, this approximating automaton returns robustness positive or zero. Yeah, this is guaranteed by the model checking. So we have this inconsistency. So this actual model always should have this negative or zero robustness, while our approximating model should be positive for any input. So by exploiting this difference, we use this heuristic, namely we try to find the difference of these two system behaviors where the robustness of this original system is small, which is something like this can be illustrated by this figure. So yeah, there are many input signals, and for each input signals, it outputs these behaviors for each of these models. And we maybe when the robustness is large, these two things can behave similarly. But our assumption is that when we go down, then at a certain stage, the robustness for this actual system can be really low because like we assume that it can go negative or zero. But the robustness for this approximating automaton doesn't go that low because of this fact. So this is our heuristics, and yeah, because of that, we suppose that this we can find the difference somewhere around here. Yeah, and especially like if we have negative robustness for these actual systems, we can always observe this difference. But yeah, this is the basic idea of the heuristics. Yes, so we suppose that we can find the difference of these two systems where where the robustness is small enough, and we can do more direct comparison. Yeah, and actually it is already available, and it is one of the future works to apply this more direct comparison. But actually, I think this kind of direct comparison has a potential issue when comparing continuous system and discrete systems, like in our setting, because like we can have more local maxima because of this discretization. So when we compare these two continuous systems, it should be fine. There can be some local minima, for example, here maybe, or like a local maxima minima can exist. But in this kind of comparison between continuous system and discrete systems, there are this many local maxima and this kind of local minima because of the discretization, and this can be a problem. Yeah, so it is a good future work to also try this kind of more direct comparison. But yeah, I think there is a potential issue. Okay, so let's go to the experiment part. So we have these three research questions. First, does this robustness-guided black box checking falsify as many specifications as baseline algorithm? The second one is which black box checking is the best. Like we have genetic algorithm and hill climbing, as well as the more basic random search based one. And the third question is the scalability with respect to the number of the specifications. So yeah, we tried these algorithms. So in addition to our these two hill climbing and genetic algorithm based robustness guided black box checking, we also tried the more standard black box checking only with random search for the equivalence testing, and we also used breach as a baseline of the state of the art falsification tool, and also the pure random search is also used to check the difficulty of the specifications. Okay, and we used this benchmark, and we have this set of the specific STO formulas as the specifications. So yeah, for example, this phi 1 consists of 9 specifications with the same STO template where the thresholds are this different. Yeah. So the motivation to use this kind of benchmark is that, like in practice, it is difficult to decide this kind of threshold. Like when we don't want to have too large velocities, but we don't know what is the too large velocity. This kind of thing almost always happens when we want to write a specification. And yeah, the motivation to use this kind of benchmark is that kind of thing. Okay, so this shows the number of the falsified properties, and this shows that robustness-guided black box checking with hill climbing and breach often fails to falsify some input specifications, properties. And random BBC also sometimes fails. It performs very good, but sometimes fails. And genetic algorithm 1 falsifies the largest number of the specifications for all the specifications. So yeah, it looks like the genetic algorithm based one is very good. For the research question 1, we can say that at least for these benchmarks, robustness guided black box checking performs as good as breach, at least. And for the research question 2, it looks like the genetic algorithm based one falsified more than the random and hill climbing. It is true, but if we also look at the time to falsify the specifications, it can change a little bit. So when some other methods rather than the genetic algorithm based one, tends not to be the fastest one. It is because genetic algorithm is a bit more complicated than the random search or hill climbing. So I think like it is really important to falsify very difficult specifications than making first for easy specifications. But it can be the case that for some situations, random search or hill climbing is still good, especially random BBS can be an option for some usage scenarios. This shows the scalability with respect to the number of the specifications in this phi 6. So this shows that in random BBC, or like basically for the black box checking, the time to falsify doesn't grow too much with respect to the number of the specifications. This is because like in black box checking, once we obtain a good enough approximating system model, we immediately falsify several specifications. This kind of thing happens. For example, here we have a discrete gap, but probably this is because of that kind of like we found a good model around here, for example, I guess. But in breach, because we falsify one by one, it's more like a linear. So this shows that black box checking is more scalable than breach with respect to the number of the specifications. Okay, so in conclusion, we introduced robustness-guided black box checking, and we used robustness for the equivalence test. And our experimental evaluation shows that it outperforms breach. This is good, but I would say that this is just the beginning of the story to exploit the system approximating model, which is obtained in the previous testing trials. Because we want to reuse the previously learned system model, system approximating automata for the other specifications. But the direct reuse just doing model checking actually didn't work. So this shows that it is indeed the case that the model checking returned this many counterexamples. But actually, they are not really the counterexample. I mean, these input signals actually did not violate the original systems for these things. Yeah, for this file, it violated, but it is really not always the case. But we also observed that the average robustness is really small. For example, 1, 2 for these kind of things. While, for example, here we see that the threshold is 90, 60, 50, 60, this kind of thing. We can say that this robustness is really small. So maybe we can exploit this information for the next time. But this is still something unclear for us. So there are several future works. So for example, how to reuse the generated media scene for the next time in a better way. And black box checking for multiple systems is another future work. Maybe the adaptive model checking is used, but yeah, it is also still a future work. And try more benchmarks to figure out some further issues is also necessary, because this is the experimental result is actually limited to this small class of the specifications with one Simulink model actually. So thanks for your attention.